x direction, and these points might have large errors on the x direction so that they're actually related to that line. So it really could be that this assumption, so this assumption was first, that was all suggested, this could also be what's wrong. Does anybody want to give another possibility of what might be wrong? Let me try. The errors might not be Gaussian. It might be that there's a large tail to the error distribution, so some points get sent off. Notice, look at these data. You can tell that at least one of these assumptions is wrong, but you can't tell which one. Right? So that's an important and strange issue. That you can see here that your generative model is wrong, but you don't know why it's wrong. And that is the typical situation in science. Right? The typical situation in science is you can see that there's stuff going on in the universe that isn't in your model, and you don't know what the hell it is. Okay, so that's the problem we're going to solve right now. So we're not going to solve that in general, obviously, because that's in general, that's a hard problem. There is no general solution to that I know about. What do you have to do? You have to decide what you care about. So let's imagine in this situation here, all we care about is the slope of the zero scatter relation. Okay? So let's imagine that we're guessing that these assumptions are minimally broken, i.e. that there is some zero scatter straight line in there, and some of the data points do obey it, and we just don't know which ones, and those ones have Gaussian errors. So let's just assume we're very close to the straight line model. What do? We still have to write down something that generates these data. Okay, so here's where I advocate mixture models. So, and this is in general a way of dealing with, there's a lot of times in astronomy, you have a data set, you think that the data set is explained basically by a model, but there's outliers, or there's irrelevant points, or there's foreground contamination or background contamination. It's a very common situation. And the mixture model is that there is some generative model for your data. So remember, the generative model is the probability of the data given model parameters. And we're going to write this as a sum. If you have two probability distributions functions which you add together to make a new probability distribution function, that's called a mixture in the business. Don't ask me why. It should be called a sum. It's called a mixture. So this is going to be a mixture of, there's a probability p bad that a data point is coming from a different distribution, a bad distribution, times the probability times my generative model for the bad points, plus there's a 1 minus p bad, and I should be careful to keep this capital P so we don't get confused, times the generative model for the straight line. And I'll call the straight line the foreground model because it's the foreground that we care about. There's this background of crazy points we don't care about. And this is the data given the parameters of the foreground model, which is a slope and an intercept. So I'm going to model my data as having some fraction of data points are just bad. See how this is an amplitude that can go from 0 to 1? There'll be an amplitude, there's a probability that the data points are bad, times some generative model for the bad points, plus the remainder probability is the probability that the points are good, and then times the model for the good points, which we're going to assume obeys these properties. Okay, so before I continue, who here has encountered the problem of fitting a straight line or other function in the presence of outliers? Who here has done that problem before? Okay, good. Anybody want to volunteer how they solved it? Don't worry, I won't make fun of you. I have also, in the literature, I've put many things in the literature which I now believe to be wrong, and I will point them out to you. Yes, how did you solve it?
Sigma clipping.
Sigma clipping. Good. Let's talk about sigma clipping for a second. So the standard way to do this in astronomy is called sigma clipping. You run this fit, and you say, which data points are outliers? By some criteria, maybe 3.5 sigma. So you take all the data points that are more than 3.5 sigma away from the line, you cross them out, you refit, then you reanalyze which ones are 3.5 sigma away from the line, you recross them out, you refit, you reanalyze which ones are 3.5 sigma away from the line, you cross them out, you refit, and eventually you converge to some solution. Does anybody want to give me a reason that's... Actually, I have to say, that works really well. But does anybody want to give me a reason why it's wrong, despite the fact that it works really well? Dustin's going.
You could be out of date at some point.
Say again?
You could be out of date at some point.
You could be out of date at some point. There's no proof that that will converge. Certainly there's no reason that that will converge. That's absolutely true. On the other hand, there's no reason in this, there's no reason when we run this model that we're going to find that p bad is bigger than 1, is smaller than 1. It might be that all our data points are bad and we're going to learn that. So that's certainly the case. Dustin, were you going to say something?
I was going to say the same thing.
Good, okay, yes?
The other problem is that you give the primitive 0 or 1 to the points you cross out.
Ah, somehow, when you're crossing out the points, you're then fitting without them, and you're not somehow penalizing the model for the fact that you've thrown them out. They should still appear there somewhere. They should be relevant to the question. So this relates to the fact that sigma clipping is a procedure. Did you hear me describe it? I described it as a procedure. I didn't describe it as an objective function which is optimized. In fact, no one knows what objective function sigma clipping optimizes. Therefore, it is not science. And the line you get out of it is not the best fit line. Because how could you say it's the best fit line? You have no objective function by which to compare it with any other best fit line that somebody else proposes. So the nice thing about an objective function, if you have this generative model and you have this objective function, you can say which of two fits is a better fit. If I start this sigma clipping at one place, it might come to one solution. I start it somewhere else, it comes to some other solution. How do I compare those two solutions? I need some objective basis for comparing those. And sigma clipping has to be wrong because it doesn't involve an objective function which you can use to then compare the models, right? Okay, so now, this, of course, I'm making up. I have invented this, but it is a generative model. So I'm making my assumptions about the data very clear. I'm assuming that a fraction 1 minus p bad of the data are coming from this set of assumptions, from my generative model for the foreground, and that a fraction p bad are coming from some other model. And of course I have freedom in choosing what this model is, so I have some freedom here, but at least I'm making my assumptions very explicit. And I'm going to be able to quantitatively compare different models. Okay? So let's make this model a little bit more explicit. So we already know that P foreground is what we wrote down before. Pi, the product over the I data points of the normal, of the Gaussian evaluated at yi, given mean mxi plus p and variance sigma yi squared. Okay, that's the foreground model. What are we going to use for the background model? Well, there's many things you could use for the background model. Let me just write down the dumbest thing that you could possibly write down for the background model. The dumbest thing is that all of the outliers are just drawn from one Gaussian. Okay, so I shouldn't, I've made a slight mistake here, which is that really I should say that this, I have made a mistake, I'm sorry about this. I should say that this is a product over I of p bad for yi and 1 minus p bad for yi. And then this just becomes, where's my pseudo eraser? There it is. The Europeans seem to believe that you erase a board using water, which violates, if I'm religious about any